Here we present to you our graduation project. Our team consists of 3 members. Cemre Şahinoğlu, responsible for software, Gülay Özalp, responsible for electronics, and Sadık Barış Günay, responsible for mechanics. In this presentation, we will cover the topics given on the slides. In the first section, we will show you a short video of our robot's operation. Then, we will talk about our scope and requirements. Our robot is designed to collect trash on the beach. It has a scoop on the front to collect trash, 4 wheels for movement on the beach, a waste container, and autonomous and RC modes. In autonomous mode, it can detect and locate waste materials, navigate towards them, and collect them. In RC mode, the robot is controlled via remote control. You can see our assumptions and requirements in this slide. We assume that the weather conditions are stable and the temperature is between 20–25 degrees Celsius during operation. Maximum waste size is assumed to be the same as a plastic water bottle. The robot will work on dry, fine sand. From our assumptions, the following requirements are obtained. The robot will weigh around 10 kilograms. In autonomous mode, it will detect the waste by a camera and move with GPS points. The color should have been white so that the robot wouldn't get too hot. The dimensions and the speed are given on the table.
In the second part of our presentation, I will talk about the mechanical design of our beach cleaning robot. Inspired by a report to share by NASA about the movement mechanism of the Curiosity rover used in the Mars mission, we switched to the design. Square holes in design served two purposes: ensuring that the vessel movements strength on the sand and allowing that sand to drain of their well in the well is full. Well movements are included in the video. In our robot, we made sure to condition the strongest forces that can occur the extreme condition. We applied these forces of the well of the robot, and the maximum force that can act the well is 200 Newton, and we determined the material uses as PLA. We used the von Mises method for this force analysis. We aimed to design a shovel with in front of the robot to dump off the garbage instead the treasure chest. We tested of the arms in shovels withstand 150 Newton and the product is using a 3D printer. The volume dimension of the shovels are shown in the table. The rack movements can be seen in the video. Which was originally planned to be made of aluminum. revised and produced seamlessly with PLA, and von Mises method was used for tensile strength calculations. This body along with other parts was produced using a 3D printer. Additionally, the production of the arm of garbage collector located of the front of the robot was also completed smoothly. The end product is shown in the video. Here the necessary calculation for motor selection can be seen. Aerodynamic forces are neglected because our speed is low. We have climbing force, rolling force, and acceleration force. The maximum slope is assumed as 10%, which is about 5.7 degrees. The calculation we made accordingly. Required power and torque can be seen on the slide.
The electronic components and design will be discussed in this part. The system consists of two main components, the agent controller and the work plan. The agent controller is responsible for the overall control of the system. The work plan component of the system is responsible for the physical action of the robot. It includes sensors such as ultrasonic, humidity, and load cell sensors that are used to gather information about the environment. Within Raspberry Pi, we are using camera. The other sensors are connected to the main controller Arduino, which processes the sensor data and sends commands to the motor driver. The step motor driver controls the step motor, which moves the arm, and the DC motor controller two DC motors, which moves the robot. The system powered by LiPo battery. Our robot is moving on the beach, so it affected by various resistant force such as climbing, rolling, and accelerating force. Since our robot moves at low speeds, air drag is not considered. Based on required torque and power, the Polol DC brush 12 volts with encoder was selected as a appropriate DC brush motor. This motor offers high torque and prestige control, making it well suited for use. Schematic design in the Proteus design suite can be seen. For driving motors, three identical motor drivers were used. There is a voltage regulator in the circuit. The sensors are attached to the header soldered to pins coming out of the main controller. The circuit soldered to the perforated plate.
In this part, I will talk about our object detection algorithm. For the creation of the dataset, videos like the one you see in this slide were recorded by the team members. The frames of the videos were saved for the dataset. After necessary adjustments and data augmentation, the images were ready for training. We trained YOLO V5 model with our custom data. Here on this YML file, you can see the number and the names of the classes of our dataset. And here you can see the code piece for the training. Since the model is pre-trained, we cloned the YOLO V5 model from the original GitHub repository to our Colab environment. Then we decided batch size as 25 and we tried with different epochs. In this slide, results for train and validation sets can be seen. On the left side, losses can be seen as they're getting closer to zero. On the bottom right, we can see that the MAP score with different IOU thresholds is getting closer to 1 as we increase the epochs. Here you can see the video that was recorded by the camera mounted on the robot. The object detection algorithm works as expected, with minor errors, and successfully detects the waste material.
Here I will talk about the autonomous mode of our robot. The block diagram of the system starts with in the input of the environment data and ends the mechanical output of wells. GPS and IMU data processed in the signal process and process data analyzed the used for localization and navigation. According to reference given to motor with path targets, the controller and control sends signals to the motor driver and control motors. An encoder uses as feedback sensors to control the position and speed the motor. For navigation, we plan use predefined GPS waypoint and RRT algorithm. A flowchart of the algorithm can be seen on this slide. Our simulation running in the gazebo environment uses LiDAR for object detection and RRT algorithm for path planning. For autonomous control and control software is excited that includes data such as the acceleration, deceleration, and turning rates of the vehicle, as well as minimum and maximum turning angles. As shown in the video, it moves along the determined route use path in the font on its own. The code has been prepared in the Python environment.
This section about our KUTERO mobile application. We develop a mobile application for customers. The mobile application allows users to control and monitor the beach cleaning robot. Through the app, users can access beach location and monitor cleaning activities in real time. They can also access the cleaning history and portfolio of the beach and evaluate the cleaning performance. The user will be able to start the system with a button after meeting the operation condition. However, this application is a testing phase. It's out of the scope, but it's a creative solution. In this part, we will explain timeline, budget, and progress chart. Our process which starts with a literature review and it ends with the implementation of the robot. You can see the process in detail in this timeline. Here you can see the final budget of our project. Show you our progress charts that includes every detail of our project. This chart helps us to see our position in the project more clearly. We divided the project in three main aspects. Here is the mechanical process. It's all done. There are things we couldn't have done in electronic parts, as well as the software part. Thank you for listening.